Hello 9th class students. The next chapter which I am going to start for you is atoms and molecules. See, when it comes to SSC examination, this chapter is very important, because in the next year you have a chapter by name structure of an atom, which is again a high weightage chapter, and when it comes to intermediate, again this chapter repeats. Okay, so the foundation which you will be receiving in the 9th class is going to help you understand the chapters in the later stages or the advancement of the topics in atoms and molecules. Okay, so I'm going to start atoms and molecules. It's a bit lengthy chapter and I'll be going in very detail for this one, so watch the videos which I'm giving you now.
Hello friends, this video on atoms part 6 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 5 before going ahead with part 6. So what is atomic spectra? What do you think can be atomic spectra? Spectra is nothing but a plural of spectrum, right? We have spoken about spectrum. What is spectrum? It is nothing but a series of different colors, somewhat like that, right? We say that when we saw that when white light was passed through a prism, we got a spectrum. What was that spectrum? It was nothing but a series of all the 7 colors which was obtained. So atomic spectra is nothing but a spectrum which is obtained from an atom. Why is it obtained? What do you do so that the atom gives rise to a spectrum? So there are many different ways by which atomic spectra is formed. So here what we are going to talk about is the different types of atomic spectra. Because why are we studying atomic spectra? First of all, because when we talk about the structure of atom, when we talked about the Rutherford's model, this atomic spectra is a very important property of atoms and it has got very useful applications in our day-to-day life. We will talk about that later. So Rutherford model could not explain this atomic spectra, and it was Bohr's model which was able to explain this atomic spectra. So in order to understand what this atomic spectra is, first you should know what is atomic spectra, right? Only then you can understand what Rutherford could not explain, which Bohr could explain. Right? So we will talk about the different types of atomic spectra, that is emission spectrum, absorption spectrum and continuous spectrum. So broadly these are the 3 types of atomic spectrum which we will talk about: emission spectrum, absorption spectrum and the continuous spectrum. We will discuss about each of them in detail. Now, what are spectral lines? In this slide, I am just making you familiar with the terms. What is atomic spectra? What are spectral lines? So, spectral lines are nothing but the series of bright and dark lines which constitute the spectrum. So, the lines of the spectrum are known as the spectral lines. So, the spectral lines look somewhat like this. This is a spectrum. This entire figure which you see here is a spectrum, and these lines which you see, the blue lines, the green, the red and the yellow lines, these lines are known as the spectral lines. And what is spectroscopy? Spectroscopy is the study of emission and absorption spectra. Spectroscopy is an extremely interesting and useful branch of science. What do we do in spectroscopy? Basically, it comes only at very higher level. You would see that scientists in big organizations, they use this different kind of spectroscopic techniques. They use something called NMR spectroscopy, some other kind of spectroscopy as well, with the help of which they try to identify substances. That means every object has a distinct spectrum of its own. Right? For example, let us suppose every human being has got a particular name of its own, but name is not unique. For example, let us take an example of any name. Let us suppose if we take the name Amit. Amit is a name, but it is not a unique name. Amit might refer to one person, it might refer to, there are hundreds of Amits, right? So it is nothing very unique to a particular individual. But for example, if I talk about fingerprint is something which is unique to an individual, right? So 2 individuals cannot have the same fingerprint. It is somewhat like that, except for very special cases, right? So similarly, the spectrum, this emission and absorption spectrum are also very unique to each particular element. So by looking at the emissions or absorption spectrum, scientists can predict which object is it, right? So this study of emission and absorption spectra is known as spectroscopy. Fine? Okay. So now let us talk about the atomic spectral emission lines. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Right? The name itself is saying emission spectrum. That means the spectrum is emitted by a substance which has absorbed energy. As I mentioned before also, whenever we talk about a substance is nothing but it is finally made up of atoms. So this spectrum is formed because we have supplied some additional energy. So the object absorbed some energy and then it emitted the spectrum. So this spectrum is known as the emission spectrum. Atoms, molecules or ions that have absorbed radiation are said to be excited. That means when we talk about the different energy levels, we talk about the ground state. Ground state means the most stable state where the atom is completely at ease. It is relaxing. It has neither absorbed energy nor it has released energy. But now once that atom absorbs some energy, it goes to a higher energy level and we say that the atom is excited, right? So whenever an atom or molecule or ion absorbs radiation, we say that it is excited. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength of the radiation emitted as the sample gives up the absorbed energy is recorded, right? So how do we produce this emission spectrum? As I mentioned, for this we will have to supply some additional energy. Now we can apply this additional energy either by heating that object, we can give heat energy, or we can give some radiation on that object. So there are different ways by which we can supply this additional energy. Now that substance will absorb this additional energy and it will emit the emission spectrum. And then what is done? Then the spectrum which is emitted or the radiation which is emitted, the frequency of that emission is recorded, right, as a function of the energy which is absorbed. So this is how the emission spectrum is formed, right? How can we generate emission spectrum basically? So this is how we generate emission spectrum. The study of emission or absorption spectra is known as spectroscopy. I mentioned it in the previous slide as well. So this is how our emission and absorption spectrum looks like. Now we got a touch of what is atomic spectra. So now this Rutherford's model was not able to explain that why this atomic spectra forms, what gives rise to the formation of the atomic spectral lines. So it could not explain that. So what were the reasons that gave rise to the Bohr's model of atom? The first one was dual character of electromagnetic radiation. Rutherford's model could not hint anything about dual character. And the second one was the experimental results regarding atomic spectra. It also could not explain anything about the atomic spectra. So in order to cover these two areas came up the Bohr's model.
Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.
Hello friends, this video on atoms part 7 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 6 before going ahead with part 7. So when we talk about dual nature of electromagnetic radiation, we mean that electromagnetic radiations possess both wave-like and particle-like properties. That means it can behave as a particle as well as a wave depending upon the situation when we are studying it, right? So we have discussed about this dual nature in our previous lesson in detail. So when we talk about wave nature, we talk about the phenomenon and the properties of the radiation like diffraction, like interference, When we talk about particle nature, we talk about different phenomena. For example, the black body radiation, the photoelectric effect. Photoelectric effect, something which we discussed in length, and it was an effect which actually brought into picture the dual nature of matter and radiation. Variation of heat capacity of solids as a function of temperature. This is something which we have not yet discussed. Maybe you will study it in your higher classes. So these are some of the phenomena or properties which support the particle nature of radiation, and diffraction and interference are some of the phenomena which support the wave nature of electromagnetic radiation. So this dual nature of electromagnetic radiation could not be explained by Rutherford's model of atom. Right? Also the line spectra of atoms with special reference to hydrogen. This line spectra also falls in the favor of particle nature, right? So these were some of the things which could not be explained by Rutherford's model, and that is why Bohr's model came into picture, right? So now there is one important question that might come in your mind, that why do we see an object when most of it is empty space? Did you understand the question? Try to understand it in this way. For example, what did I mention? I told that Rutherford in his model has stated that most of the space inside the atom is empty. The only dense region is the nucleus, and that nucleus is a very small region, right? So if that entire atom is empty, it is like there is nothing inside that atom. So whatever object which we see in front of us, let us, in this case we have taken the example of this wall. This wall, what is it made up of? It is made up of huge number of atoms. Now all of these atoms are empty. I mean, it is like, you can imagine it like transparent walls. So now if an object is made up of transparent walls, that object should also be transparent. Then why do we see this wall? Why are we able to see this wall as an opaque object when it is made up of something which has got lot of empty space? In order to understand this, you have to take this example. If you look at this netted wire, right? If you take the example of this cat, if the cat wants to pass through this netted wall, will it be able to cross the net? No. Why? Because the dimension of the net, or the dimension of the open space in the net, is smaller when compared to the dimension of the cat. The size of the cat is bigger, so it cannot pass through, right? But if you take the example of this small insect, what happens for this insect? The size of this insect is very small when compared to the dimension of this open space. So the insect will be able to pass through. So for this insect, if it looks at this portion, for this insect it is nothing but empty space. But for this cat, it is not an empty space. For this cat, it is a netted wire, right? So it all depends upon the relative dimension with which you are observing a particular object. So the same netted wire, when viewed by an extremely small insect, he would see it as an open space. For him, there is no netted wire. When the insect reaches this point, he could see all around itself open space. So for him, it is open. There is no netted wire which it can see. But when this cat sees it, for him, it is a netted wire and the cat cannot pass through it. Similarly, when we talk about this wall, which we say is made up of a huge number of atoms, which is nothing but empty space, end of the day. But since the number of atoms are huge, and also the ray which is being used to make it visibility, for example, we are able to view objects, or our visibility is because of the light rays, right? Because of the visible light. So the wavelength of that visible light also plays an important role. So the wavelength of the light is nothing but the examples which I have taken here. So here in this case, this netted wire is nothing but this wall, right? Now, if I am viewing this wall with the help of visible light, the order of the wavelength of the visible light, if it is comparable to that of the dimension of the atom, because the dimension of the atom is very small, right? So if the wavelength of the light is comparable to the dimension of the atom, in that case we would be able to see it as what it is. I mean, in that case we will be able to see it as transparent or open space or empty space. But since the wavelength of light with which we are observing it is not at all comparable to the dimension of the atom, the dimension of the atom is extremely small, therefore we do not see it as empty space. So this would be the best example to understand this case. So it all depends upon the reference which you are using. So reference in this case is the wavelength of the visible light, because we are observing the wall because of the visible light, right? Okay, so this was out of the track, I know, but I just mentioned it because it might come to your mind, because we have always been talking about this fact that atom has lot of empty space and all.
Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.
Hello friends, this video on atoms part 8 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 7 before going ahead with part 8. Now let us come back to Bohr's model of atom. So let us see what did Bohr do to incorporate the limitations which were there in the Rutherford's model of atom. So Bohr's model of atom told that it used the emission spectrum of hydrogen to develop a model for hydrogen. So Bohr's model of atom basically focused on the model of hydrogen atom. This again became a drawback for the Bohr's model, but however for hydrogen, Bohr could explain everything to a very large extent, right? So what did Bohr do? He used the emission spectrum of hydrogen, and with the help of that spectrum, he developed a model for hydrogen atom. He postulated that electrons move around the nucleus in circular orbits. Okay, this was something similar to what Rutherford had told. Bohr model determines the radius of each circular electron orbit. Okay, so even Rutherford had told that electrons are moving in circular orbits. Bohr calculated the energy of electron in various orbits, and for each orbit predicted the distance between the electron and the nucleus, right? So in case of Bohr's model, he mentioned the exact energy orbits which the electron can occupy. It is not that electron can occupy just any orbit. So there are some specific orbits in which the electrons can revolve around the nucleus. So it offered a satisfactory model for explaining the spectra of the hydrogen atom. So this was a major drawback of the Rutherford model. Only certain orbits can exist, and each orbit corresponds to a specific energy. Electron energy is quantized, right? So Rutherford never talked about quantization, but Bohr told that it is not that electron can revolve around the nucleus in just any circular path. It is not like that. There are certain orbits, or there are certain circular paths only through which the electrons can revolve around the nucleus. So that means the energy, electron energy, is quantized. Electron energy is not continuous. It cannot be just any value. It can only be, there are a set of discrete values which are only allowed, right? So these were some of the postulates of the Bohr's model of atom, and with this we will start understanding Bohr's model. So before that, we will get a little more knowledge on atomic spectra, because if you are not very much clear with the different types of atomic spectra, it will become difficult for you to understand the postulates of the Bohr's model. As I mentioned, Bohr started his theory with the emission spectra of hydrogen atom. So for that, you should first have a bit more idea on the atomic spectra. So now we will discuss about the different types of atomic spectra in detail. So before that, let us talk about continuous spectrum and quantized spectrum. What is a continuous spectrum and what is a quantized spectrum? So let us talk about the continuous and quantized spectrum. So what is before we talk about spectrum, let us just differentiate between the two terms, continuous and quantized. When I say continuous, I mean a value which keeps changing continuously. Let us suppose right now it is at this point, then it is at this point, here, here, here. So if you look at this value, this is changing continuously, right? So at every instant, it has got a different value. So it is changing continuously. Whereas if you look at a value like this, so in this case, if you see at every point, it has got a distinct value. It is either high or it is low. It is either high or it is low. So that means it has got some discrete set of values. I mean, we talked about continuous and quantized when we were talking about analog and digital signals. You remember? So when we were talking about digital signals, we said that it can take only two values, either 0 or 1. So that means there are a discrete set of values which are only allowed. It cannot take any other value except 0 and 1. So similarly, in case of continuous spectrum and quantized spectrum, when I say continuous spectrum, that means the energy can take any value. Energy can be 1, energy can be 1.2, energy can be 5, energy can be 10, energy can be any value. But when I say quantized spectrum, that means there are a certain values of energy which are allowed. Let us suppose if the allowed energy values are 1, 2 and 3, it cannot have any other value except those 3 values, right? So quantized spectrum means a spectrum which consists of spectral lines, very specific spectral lines. That means it has got only discrete allowed spectral lines, whereas a continuous spectrum means it has got a spectrum which does not have discrete lines. It has got a band in a continuous range, right? So if you look at this continuous spectrum, here what do you see? You see that here it is dark, it gets lighter, 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 and here it is light, right? So it is changing continuously. But in this case, if you see, there are discrete lines at places. So that means when I talk about quantized spectrum, we are talking about specific values. When we are talking about continuous spectrum, we are not talking about specific values. So look at this example, which will make your understanding even clearer. In the first, you see that there are no stairs. It is a continuous change. I mean, the girl reaches from this point to this point. That means here also the girl travels this height h. But in this case, there are no discrete energy levels. It is changing continuously. But in this case, there are discrete levels. 1, 2, 3, 4. So there are 4 discrete levels which are only allowed. So the girl is allowed to step only on these 4 stairs. So she cannot step somewhere in the middle of these 2 stairs, right? So these are the 4 stairs where she is allowed to step. So this is your quantized spectrum. In this case, the girl is allowed to step anywhere she wants, right? So it is changing continuously. So this is a continuous spectrum. Now, why are we talking about quantized spectra? That's because when we look at the atomic spectra, we see that there exists spectral lines. So whenever we see distinct spectral lines, we are talking about quantized spectrum. So this is the evidence for the quantized electronic energy levels. So atomic spectra becomes an evidence for the existence of quantized spectra. So now let us discuss each of this spectra in detail. So we will talk about continuous spectrum, emission spectrum and absorption spectrum. Let us start with continuous spectrum. It is observed when a ray of white light is passed through a prism, the wave with shorter wavelength bends more than the one with a longer wavelength. We have discussed these things in detail, right? We have talked about the phenomenon of dispersion of light in one of our earlier lessons, right? So the spectra which we obtain in this case is a continuous spectra. If you see, it is not, you are not able to see any discrete line, right? It is like gradually the violet becomes blue and then the blue becomes yellow, it becomes red and so on. So that means the change in the colors, it happens gradually, right? So this kind of spectra is known as a continuous spectra. The speed, in this case, why this spectra happens, that we already know, right? Because white light consists of many different colors, and each of these colors has got a specific wavelength. Now, each wavelength, when they pass through the prism, they get deviated at a different angle. So because of these different angles of deviation, they get deviated in different ways. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. We have discussed this dispersion of light in detail, so I will not spend more time on this. The light of red color, which has longest wavelength, is deviated the least, while the violet light is deviated the most. The next one is the emission spectra. The spectrum of radiation emitted by a substance that has absorbed energy is known as emission spectrum. That means whenever you supply some energy to a substance, it gets excited, as I mentioned before also. I mean, when you do not supply any energy, every object is in its ground state. That is the most stable state. Most stable state means the state of minimum energy, right? As soon as you supply some external energy, what happens? That atom goes into the excited state. By absorbing this energy, that atom emits a radiation. So that radiation is known as, or that spectrum is known as the emission spectrum. So the spectrum of radiation emitted by a substance that has absorbed energy is called emission spectrum. To produce an emission spectrum, energy is supplied to the sample either by heating it or by irradiating it, and the wavelength of the radiation emitted as the sample gives up the absorbed energy is recorded. That means, let us suppose this is the substance. This is your substance. You give some energy to this substance. So what happens? This substance will absorb this energy and give out emission spectra. So this emission spectra is the result of the energy which is absorbed, right? Let's look at the absorption spectrum. An absorption spectrum is like the photographic negative of an emission spectrum. As I mentioned, whenever we supply some energy to an object, this is my object, I supply some energy E to this object. So this substance is absorbing the energy. So some energy it will absorb, and the remaining will be emitted as emission spectra. Now what about the energy which is absorbed? So the energy which is absorbed, that is given as the absorption spectrum. It is somewhat like this. Let us suppose you have there is a 10 rupee note in a drawer, right? There is a 10 rupee note in a wallet. The wallet is right now placed on a table. So the 10 rupee note is intact. Now this wallet comes to your hand, right? So in this case, you are the subject. I mean, you are the substance now. Now as soon as that wallet comes to your hand, what happens? Out of those 10 rupees, you take 5 rupees. So how much is left? 5 rupees. So the remaining balance is 5 rupees. Now the wallet again goes back to the table. But now what is there inside the wallet? It is 5 rupees. So what happens to the remaining 5 rupees? It is absorbed by you. So this remaining 5 rupees, here is the amount which is absorbed. So whatever is absorbed is given as, or is emitted as, absorption spectrum, and whatever is remained is given as the emission spectrum. So you understand the difference between emission spectrum and absorption spectrum? The incident radiation falls on an object. Some part is absorbed, which is given as absorption spectrum, and the remaining part is emitted as emission spectrum. Therefore, it says that the absorption spectrum is like a photographic negative of emission spectrum. That's because whatever is not present on the emission spectrum is present on the absorption spectrum. Here, 5 rupee was missing. So where is that missing 5 rupee? It is in the absorption spectrum, right? So an absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelength. The missing wavelength, which corresponds to the radiation absorbed by the matter, leaves dark spaces in the bright continuous spectrum. You understand it in this way. This is how you get your absorption spectrum. What does this mean? That means that these lines represent the radiations which have been absorbed. So that means whatever your incident radiation was there, from that incident radiation, only these parts, if you subtract, the remaining will be your emission spectrum. So if you think of an emission spectrum, it will be just the reverse of this. In case of emission spectrum, these areas will be dark and the remaining areas will be bright, right? So let us have a comparison of all the three spectrum. So when I talk about continuous spectrum, it is somewhat like this. You don't have distinct specific lines, right? So this is my continuous spectrum. That is clear. When I talk about emission spectrum and absorption spectrum, what is the difference? When I talk about emission spectrum, I have got specific lines, right? Like whatever my incident was, whatever my incident radiation was, the same was absorbed except the one which are absorbed. So what is absorbed here? Now in emission spectrum, these are my dark areas. That means these are the missing areas. Now where are these missing areas gone? They are in the absorption spectrum. So this is my absorption spectrum. So the absorption spectrum will be bright where the emission spectrum is dark. Right? It is similar to the example of the 10 rupee note example. So you had 10 rupees in the wallet, you took out 5 rupees. So remaining is 5 rupees. So this emission spectra is the remaining balance. So in emission spectra, if you see so many black region, that means these are the regions which are missing in the emission spectrum. That means these regions will be colorful in the absorption spectrum, right? So this is the difference between emission spectrum and absorption spectrum. So I hope I am able to explain you what are the different types of spectrum.
Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.
Hello friends, this video on atoms part 9 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 8 before going ahead with part 9. Now, what is the significance of this spectral lines? As I mentioned, this study of spectrum, that is spectroscopy, is extremely useful. How? Because line emission spectra are of great interest in the study of electronic structure. This line spectra can help you to identify elements. By looking at the spectrum produced by a substance, you can identify the substance. Each element has a unique line emission spectrum. This is what I was talking about some time back. I told you, right? Like every human being has got a unique fingerprint. So by looking at the fingerprint, you can identify it belongs to whom. Similarly, by looking at the line emission spectrum, you can identify which element emitted this spectrum. The characteristic lines in atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. Very true, right? So where does it find its applications? For example, I'll give you one small example. Let us suppose there is some atom bomb or some poisonous substances created by some bad group of people, right? So they are using it for some bad purpose. They are using some poisonous chemical to kill people, right? So now there are a group of good people who want that chemical to be detected, right? Now if that chemical has come into market, many people will buy it and will make bad use of it, right? So how will you be able to detect that chemical? Because by looking at it, you will not know what it is. So how do people do research on this? They take that chemical, they try to study the spectrum formed by that chemical. By looking at the spectrum or by studying that spectrum, they are able to identify the constituent of that chemical. They are able to identify how that chemical has been composed of. Now, once you know the constituent of the chemical, then you will be able to find out a solution which can fight with that chemical or which can destroy that chemical, right? So this is how line spectra is used to identify elements. There was a German chemist named Robert Bunsen, was one of the first investigators to use line spectra to identify elements, and it is extremely useful even today. If you talk to some scientists or who are working on identification of elements, or who are doing research on spectroscopy, they will tell you how useful it is to study the structure of electronic, to study the structure of atoms. Elements like rubidium, cesium, thallium, indium, gallium, helium and scandium were discovered by spectroscopic methods, because it was found that there was some spectra which did not belong to any of the existing elements. So a new element got discovered. So this is how some of these elements were discovered. So now you understand the importance of atomic spectra? Okay. So now, since atomic spectra was so very important and Rutherford's model of atom could not explain atomic spectra, so it was a great setback for that model. Therefore, Bohr's model came up, and Bohr started his investigation, or he started his analysis from the spectra of hydrogen. So with the help of the spectra, atomic spectra of hydrogen, he gave his entire theory of atoms.
Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.